our senses paint a limited picture of reality. We see the steam rising from a hot cup of coffee, but we don't see the frantic dance of trillions of water molecules. This is where the concepts of macrostates and microstates come in. These concepts are fundamental to physics. They help us understand the behavior of matter at its most basic level. A macrostate describes the overall properties of a system that we can observe. Temperature, pressure, and volume are examples of macrostates. They give us a snapshot of a system's condition. These properties are visible to the naked eye. We can measure them with instruments, but beneath the surface of every macrostate lies a hidden world of microstates. A microstate describes the specific arrangement and energy of every single particle within a system. These arrangements are constantly changing. They are impossible to track individually. Let's take our cup of coffee as an example. Its macrostate can be described by its temperature. Let's say a steaming 80 degrees Celsius. This single temperature tells us about the average energy of all the water molecules in the coffee. The darker color of the coffee indicates a high concentration of dissolved coffee particles. The volume of the coffee, perhaps 250 milliliters in a standard mug, represents another macrostate. We can easily observe and measure these properties. They provide a practical understanding of the coffee's current state. These macroscopic observations, however, do not reveal the full story. They don't tell us about the individual journeys of the countless molecules within the coffee. For that, we need to delve into the realm of microstates. Zooming into the microscopic level of our coffee, we encounter a world of constant motion. Each water molecule possesses kinetic energy. They move around freely within the coffee. The higher the temperature of the coffee, the faster these molecules move. They collide with each other billions of times per second. The precise position and velocity of each water molecule at any given moment constitute one microstate. The coffee, as a system, has an astronomical number of possible microstates. Each microstate corresponds to the same macrostate, a cup of coffee, at 80 degrees Celsius. Imagine trying to track the movement of even a single water molecule in this chaotic dance. It's an impossible task. Yet, it is these countless ever-changing microstates that give rise to the macroscopic properties we observe. What happens when our coffee cools down? Its macrostate changes. The temperature drops, perhaps to a more drinkable 40 degrees Celsius. This change in macrostate is accompanied by a shift in the possible microstates of the system. As the coffee cools, the water molecules lose kinetic energy. They slow down. The once frantic dance becomes more subdued. The number of possible arrangements of molecules with lower energy decreases. The same principle applies when we consider a melting ice cube. The transition from solid ice to liquid water represents a change in the macrostate. This change is reflected in the arrangement and energy of the water molecules at the microstate level. The concept of microstates might seem unnecessarily complex. Why delve into the invisible world of molecules when we can easily describe a system by its macrostate? Well, the answer lies in understanding that the macroscopic properties we observe are merely averages over a vast number of microscopic possibilities. The macrostate provides a simplified view of a system. It averages out the complexities of the underlying microstates. For many everyday purposes, this simplified view is sufficient. However, to truly understand the behavior of matter, we need to consider the microstates. While we cannot track every single microstate, We can use statistical mechanics to predict the most probable macrostate of a system. This branch of physics uses probability to understand how systems evolve over time. Consider a box filled with gas molecules. Each molecule can have a specific position and velocity. This vast number of possibilities makes it impossible to determine the exact microstate of the gas. However, we can use statistical mechanics to calculate the probability of finding the gas in a particular macrostate. For example, we can calculate the probability of finding all the gas molecules concentrated in one corner of the box versus being evenly distributed. The concept of microstates is also crucial for understanding entropy, a fundamental concept in thermodynamics. Entropy is a measure of the number of possible microstates corresponding to a particular macrostate. A system with high entropy has many possible microstates. It is considered disordered. A system with low entropy has fewer possible microstates. It is considered ordered. The second law of thermodynamics states that the entropy of a closed system always increases over time. This means that systems tend to evolve towards states of higher disorder. This is because there are simply more ways for a system to be disordered than ordered. Think about a deck of cards. There are many more ways for the cards to be shuffled randomly than to be arranged in a specific order. The concepts of microstates and macrostates extend far beyond our everyday experiences. They are fundamental to our understanding of the universe at its most fundamental level. In cosmology, these concepts help us understand the evolution of the universe from the Big Bang to the present day. In quantum mechanics, the very act of observation is thought to collapse the wave function of a particle, essentially selecting one microstate from a superposition of possibilities. This highlights the profound connection between the observer and the observed in the quantum realm. As we delve deeper into the world of microstates and macrostates, we open up new avenues for scientific exploration. Advances in fields like nanotechnology and quantum computing rely heavily on manipulating matter at the atomic and subatomic levels. These manipulations directly influence the microstates of these systems. By understanding the relationship between microstates and macrostates, we gain unprecedented control over the building blocks of matter. This control could lead to revolutionary technologies and a deeper understanding of the universe we inhabit. The journey into the invisible world of microstates and macrostates is far from over. It promises to be an exciting and rewarding adventure for generations to come.